Uh, Greetings. My name is Dr. K. The GOAT. So today's lesson will be focusing on differentiation. I believe it's something that you guys have seen before. I think even from your grade 12 question paper. Remember that the last time we spoke about first principles on how we did limits, showing you how does limits work and first principles, and we got to build on that to define differentiation. So the other kind of differentiation that you guys get to do are these two types, but normally you guys you get to factorize the numerator. Remember that another notation for differentiation, we normally write it as ddx to say that you're differentiating. So if you look at what we have here in the numerator, we can factor that out, factorize it. So we end up now with x minus 3, then x plus 1, and in the denominator, we already have x plus 1. So this is normally how you guys get to do it, then cancel the x plus 1, then just get to differentiate x minus 3, which it just becomes 1. So basically the kind of examples that you guys would do, or the kind of exercises that you guys would do most of the time were those introductory, you could say that, easy examples. So now I want to look at the concept of differentiation and try to expand on that. So basically that's what we're doing today, and get to work on some rules. So basically, like I said, we're going to be working on differentiation, and basically we'll be developing some different rules of differentiation that help us to differentiate easier instead of having to factorize all the time. So they can just be able to differentiate right away. Remember that these rules can be proved by using the limits. I believe we did limits, we did limit laws. So all these rules that you're going to be developing, they are based on, they can also always be proved. So these slides, so we're going to start first by introducing some simple differentiation rules. We can prove some of them. Then we get to build on that and get to do more sophisticated rules of differentiation. So let's start first with the rules of differentiation. I believe you already know that whenever you differentiate a constant, you get a 0. Remember that, maybe remember that differentiation, basically we talk about a slope. And whenever you have a function y is equals to c, this is a constant function. So basically, it's a function that looks like this dotted line. So it's just some horizontal line. So the slope, there's no slope, because remember the slope talks about the steepness. So there's no steepness. So that's why we say that the slope of a constant function is 0, because there's no slope. So whenever you differentiate a constant, you get a 0. So we have what we call the power rule, whereby whenever you have a variable to the power exponent n, whereby n is an integer, for now, let's say is an integer. So x to the power n, so you get to, according to the differentiation rule, we drop the n, then subtract 1 from that exponent so that you can have a new exponent. So you drop whatever coefficient that you have here, you get to multiply with the exponent. So as you can see, our coefficient here is 1. So 1 times n, it gives us n. Then you get to subtract 1 from this exponent. So hence we have n minus 1. And this becomes the derivative of x to the power n. We have another power rule, which is general. So like I said here, we said if this is an integer, but actually generally n can be any real number. This can be proven. So if ever n is any real, so basically a variable to any number is equals to drop that exponent, then subtract 1 from that exponent, so that you can have x to the power n minus 1. So these are the rules. So if you get to continue with them, so whenever you have a function, multiply by some constant. So whenever you want to differentiate this, you can factor out the constant, then get to differentiate the function. We'll get to explain why this is true. We have also what you call the sum rule. So sum rule basically saying that if whenever you have functions that have been added and you want to differentiate them, so basically you can differentiate the functions individually, then add them to get their derivative. So basically saying that the derivative of a sum is the sum of the derivatives. So basically that's what we're saying here. And the same thing as the difference. So basically the differentiating the difference of the functions is something as the derivative, the difference of the derivatives of those functions. I hope that is clear. So let's just prove one. So whenever we want to prove x to the power n, so to prove this, so we want to prove that this indeed it is true. So maybe let me give you an example. So we want to basically factorize. So let's go through some factorizing. Remember the difference from two squares. Whenever you have x squared minus y squared, I believe we know that this is a difference of two squares. So whenever you get to factorize here, you get x minus y, x plus y, x plus y. So maybe to give it, let's use numbers. Let's say you want to say x squared minus say 81. So x squared minus 81, we know that this will be x minus 9. The reason being 9 times 9 is 81, or 9 squared is 81. Then here we end up with x plus 9. So even if you had x to the power 4 here, so it means that here we have x squared minus 9 and x squared plus 9. So as you can see, x squared minus 9 can be factorized further into x minus 3x plus 3. So basically, I'm talking about differentiating difference of two squares. And actually, even when you get to cube, it's the same thing. For example, if we have x cube minus y cube. For those who know, for you to be able to factorize here, you end up with x minus y. Then in the second bracket, you take the first variable, so end up with x squared. Remember that whenever you have a minus here, then it becomes a plus. Then you get to multiply the variables. So x times y, it gives us the xy. Then here is always plus, then this variable squared, so y squared, we end up, sorry, y squared, yeah, we just get y squared. So like I said, you start from the x cube minus y cube, you start with x minus y, just removing the cube. Then the second bracket, you take the first variable squared, then the last item, the last variable squared. So for you to get the middle term, you just say that those two variables multiplied together, you get xy. So like I said, if whenever you have minus here, you get plus. But this is not a lesson on factorization, but this is basically I was trying to remind you on how to differentiate, to factorize whenever you have a difference of some variables that are cubed or that are squared or have some exponent. So basically it means that if whenever you have x to the power n minus a to the power n, this is how you get to factorize it. So you end up start first with x minus a, there it is. So the first variable becomes x to the power n minus 1 plus, and now you start multiplying x minus 2 times a, just like that. Then the last item here, with this a to the power n minus 1. So whenever you get to multiply these out and you try to expand, it will take you back to the left-hand side. You can try that at your own time. So, so for any number, remember that so basically from what we have here, so now after you get to factorize this, remember that, let's talk about this a to the power n, the power rule. So from the power rule, we know that f prime at a, remember that we did differentiation. So f prime at a, this is the definition of finding the derivative at a point. Remember, there's a differentiation of a function, then there's a differentiation at a point. So this is the definition of a derivative at a point. So remember that our function, we said is x to the power n. So remember that we're trying to differentiate x to the power n, x to the power n. So basically this is our f of x. So now our f of x, we can substitute a to the power n. So f of a means that whenever we see x, we substitute a, so it becomes a to the power n. So in the denominator, we have x minus a. So this is what we have. So now, as we already spoken about factorizing the numerator here. So now expanding or factorizing the numerator, this is what we have. So as you can see, we have x minus a, of which we can cancel out, and after canceling it out, and then we'll be left with this second bracket in the numerator. So this is what we have. So now we want to evaluate the limit, because remember here we cannot evaluate the limit because x is approaching a. So if we get to substitute x as a, we end up with having 0 undefined. So now we've been able to remove the discontinuity. So now, because we cancel the x minus a, so we can be able to now evaluate substitute x is equals to a, because now we have a polynomial. So substituting substituting there, this is what we end up. But remember that x is approaching a, so since we have nothing undefined here, so it means we can substitute x is equals to a, because when substitute x is equals to a, we don't have any anywhere whereby we have undefined. So we can substitute x equals to a, so it means that here we end up with a to the power n, a to the power n minus 2 times a, just like that. So basically we have something like this. So remember, from the rules of exponents, we can be able to remember this is to the power 1. So simplifying there, it basically means that you have a to the power n minus 2 plus 1, which basically gives you a to the power n minus 1. So same thing here, we have n minus 2 times a. So all these terms will give you a to the power n minus 1. So adding all of them, remember there's n times of them. So it basically means that now there's n times of them. So this is the same thing as n times a to the power n minus 1. So in conclusion, it means that f prime at a is n times a to the power n minus 1. So if we don't want, we still want it to be general, so it means that f prime at x is going to be n times x to the power n minus 1. So this is why we say that the derivative of x to the power n is n times x to the power n minus 1. So although we said this power rule works for n being a positive integer, actually we can prove it further. It actually works for any real number. So that's why we get to call it now, instead of calling it the power rule, we just get to call it the general power rule, because whenever you have x to the power n, then n does not need to be an integer or a counting number or a natural number. Actually, n can be any number. Actually, any real number. Let me not say any real number, because being a complex number is something else. So n can be a real number. And whenever that, we just get to call it the general power rule, because this still holds when n is a real number. We spoke about the sum rule. So maybe just to go through a quick proof, I want to prove that actually the derivative of the sum of the function is the same thing as the sum of the derivative of those functions. So basically, let's call this f plus g, give it a capital F function f. So this capital F is f plus g. So now we want to differentiate this f. Remember that from the definition of differentiation, or we could say from first principles, this is how we get to differentiate or find f, capital F prime. So now, if we get to substitute, remember that capital F is small f plus small g. So since all this is capital F at x plus h, so substituting means that this is what we have. Then this capital F, it becomes f plus g. So now from with the power of associativity, we can move this minus f of x, get to come and associate it with this f of x plus h, and take this g, add it with this g, g at x plus h. So that's what we just did. So remember that according to the limit laws, then we can be able to distribute this, and this is what we have. So we can evaluate the limit, and as you can see from here, this is by the definition, this is f prime, and this is g prime. So already, as you can see, so basically we just proved that actually the derivative of the sum is the same thing as the sum of the derivatives. So same thing as the difference rule, it works the same way. So there's more challenge. I know that this proof that seems easy, but actually there's some more challenging proofs that you'll see somewhere along, especially when you get to trigonometry, when you get to differentiate your sine function, your cos function, your tan function. So some of those proofs, they are a bit challenging, but yeah, we'll get there. Let's take for an example. So we want to differentiate, find f prime from this using the power rule. Remember that square root of x is x to the power half. So it means that the exponent now, the real number here is 1 over 2. So you have x to the power 1 over 2. Remember we said the rule says you drop the exponent, then subtract 1. So basically f prime will just be dropping the exponent, which is half. So half times x to the power half minus 1, which just becomes 1 over 2. So remember that half minus 1, we end up with x to the power minus half. So changing this to be a positive exponent, we end up now with 1 over 2 times, because we want to make this exponent to be positive, it becomes 1 over x to the power 1 over 2. And remember that x to the power 1 over 2 is something as square root x. So hence we have 1 over 2 times square root x. So we have 1 over 2 root x. I hope that is clear. We have another example here. We also find y prime, whereby y is given by x to the power 4 plus pi to the power 4. But now this shouldn't confuse you, because remember that pi is a constant. So it's just a real number. So even pi to the power 4 is still a real number, is still a constant. And remember we said differentiating a constant, we get 0. So basically means that now we can, this is the sum of the two functions. We have a function of x to the power 4 and another function of pi to the power 4. So we can distribute this and differentiate x to the power 4 aside, then add it with it differentiating pi to the power 4. Now differentiating that, remember that here we use the power rule. 4, we drop the 4, then subtract 1, we end up with 4 times x to the power 3. Sorry about that. Here differentiating a constant, we get 0. So obviously 4 times 4x cubed plus 0, we just get 4x cubed. I hope that is clear. Please stop me if I'm quick or if ever there's a part that you don't understand. We have another example. As you can see from here, this is pure power rule. So I'm going to skip this because as I'll just scroll through the slides, because there's a number of concepts that I want to go through and that I need to ensure that actually we understand. So I believe the power rule is the most easiest. As you can see, we have the sum. We have we could say this is our f of g minus g plus h. So already have a rule on what do you do when you have different functions like this. So you treat these functions individually, then use the power rule, then add them and subtract them back again, because we did the sum rule, the difference rule. So basically, so like I said, we can factor out the constants, then differentiate, and this is what we get. Remember the differentiating a constant, we get 0. Differentiating x to the power 6, we drop the exponent, and then subtract 1 from 6, we get 5. Same thing as 14, we drop the 14, but you have to multiply the exponent that was, sorry, the constant, the coefficient that was there. So 9 times 14, we get 126. And yeah, add and subtract the terms again, and that's what we get. So maybe let's get a bit of a practical example. So we've been given a function y is equal to 5 over x, and we're asked to find the equation of a tangent. If you remember, we said a tangent, it's when we have a straight line that touches the function once and passing. If ever the function touches the if ever your straight line touches the function twice, that one is called a secant. Then if ever it touches once, like the straight line, I know that it doesn't look like a straight line, but I hope you get the gist. So this is what we call the tangent. So basically, you're asked to find the equation of this tangent. So now, from this function, so we're going to use the constant multiple by in terms of factorizing out the coefficient, then use the general power rule so that we can be able to find y prime, because we need to find the gradient first, then we'll find the equation later. So differentiating 5 over x, we can factor out the 5. We're going to be left with, so basically this, we differentiate with d dx, we're differentiating 1 over x. So basically that's what happened here. So differentiating 1 over x is something as x to the power minus 1. So differentiating x to the power minus 1, remember that you drop the exponent, the minus 1, then subtract 1 from it. So minus 1 gives us minus 2. So 5 times minus 1 gives us minus 5. Then making this exponent to be positive, we take it to the denominator, and that's what we have. So now we have our derivative, but remember that we are looking at this specific point. So x is 1 at that point, so we have to substitute 1 here, so you end up with minus 5 over 1 squared, which is 1 squared is 1, so minus 5 over 1 gives us minus 5. So it means that the derivative at that point will be minus 5, which will be the derivative of the tangent at that point. So now we can substitute y squares mx plus c, which is the equation of a straight line. So we already have our gradient, which is 5. Our x and our y, they'll be coming from the 1, 5, the point that we're given. So basically we're looking for the for c. So substituting, we get c, that is 10. So it means that now the equation of a tangent is y is equals to minus 5x plus 10. I hope that is clear. So as you can see, these are the function of 5 over x, the hyperbola. That's how it looks like. And this point 1, 5, there it is. So as you can see, the tangent is at this point. There's the tangent, and the equation of a tangent is minus 5x plus 10. We have another example here, but I just want to emphasize on this part, especially to talk about this e. Please don't think of this as x and get to wonder where does your x come in mathematics, and start saying stories like, hey, this is why mathematics is hard, because you're busy talking about our x's. So this is not x. So basically this e is a constant. There's a number e, it's a constant. I think it's 2.71 something. It's some irrational number. It's a very special number, but we'll get to talk about it on where does this number come from and why is it special. So we'll talk about it later in this session, but otherwise, so I was just emphasizing that don't see this as ex. This is basically, this is the constant e times the variable x. So we're using the power rule to differentiate that. So since well e is the coefficient, so differentiating x we get 1, so hence we end up with minus e. So differentiating 1 we get 0, and yeah, this is what we get from differentiating that. So if ever I'm too quick, please try to do it slower. You have to get the same answer. And we are asked to find the first, the second, and the third. So to get the second derivative, it means that we differentiate this what we have here again, and differentiating this is what we get. And to get the third derivative, it means that we have to differentiate this again. So differentiating minus 6x plus 1, we get minus 6. Yeah, so that is about the power rule. I want us now to talk about this exponential function, to the derivative of exponential function. So let's start first by talking about this function, a to the power x. So remember that by the definition of an exponential function, so meaning the derivative of this f of x will become, this is the definition, f of x plus h minus f of x. So if you get to substitute, remember that it means from the function of f of x, wherever you see x, we replace it with x plus h. So it means that now we have now a to the power x plus h. So our f of x is just a to the power x. So using the exponent rules, we can break this to a to the power x times a to the power h. So from here, we can believe we can see that we have a to the power x here, x to the power x, of which we can factor it out. We left with a to the power h minus 1 all over h. So as you can see now, we're evaluating the limit here, and this limit talks about h approaching 0. So basically it means that a to the power x is not affected because a is not h and exponent is x, it's not h. So basically this a to the power x, we can factor it out and basically get to evaluate the limit as h approaches 0 of a to the power h. So I hope you remember when you're talking about derivative as a function, what does this mean? I believe you remember. If you don't, please go through your slides again to go look at it. But otherwise, remember that our function is f of x is a to the power h. So basically, if you think of this as f of, let's say, f of 0. So f of 0, it means that this will be a to the power 0, which is equals to 1. So if you think of this f prime at 0, basically, remember that f prime at x, let me just go through, f prime at x is x plus h. So if we say f prime differentiating f of 0. So basically it means that f prime at 0, it becomes the limit. I'll just get to explain that now. H approaches 0. So it means that here we'll end up with f of 0 plus h minus f of 0. This is all over h. So obviously 0 plus h is h. So f of h, remember that we have given that f of x is a to the power x. So it means that f of h will be given by a to the power h. So hence we have this a to the power h here. Then f of 0, as we said, f of 0 is a to the power 0, which is 1. So this is where the 1 comes from. So that's why we say that this gives us f prime at 0. So, so now if we get to look at our differentiation, remember that we had factored out a to the power x. And here we said this is f prime at 0. So in other words, it means that whenever you differentiate a to the power x, we end up with a to the power x times f prime at 0. I hope that makes sense. So the question is, what does this mean? So basically, it means that the rate of change, remember that's what derivative means, is the rate of change. So basically, the rate of change of the function at any point, remember that x is any point, could be any point, is proportional to the value of the function at that point. So as you can see, the derivative of a to the power x is times a to the power x times f prime at 0. So basically, that's what this means. So basically, if we get to question this, remember that we're differentiating a to the power x, and here we get a to the power x times f prime at 0. So the question arises is that, is there a way for this f prime at 0 to be 1, such that a to the power, the derivative of a to the power x is just the same thing as a to the power x? So one could wonder that, is there a way? Because now we've seen that generally, whenever you differentiate a to the power x, we still get a to the power x times f prime at 0. So the question is, what happens, what kind of function, or what should that a be, such that that f prime at 0 just becomes 1, such that now the derivative of a to the power x with that a being that constant is same thing as a to the power x. So that's basically what we are saying here. So we are saying that now, when you get to do investigation, we get to see that actually there's some number between 2 and 3, such that at f prime at 0, it becomes 1. Basically, it means that, remember that f prime is a gradient. So we're saying that the gradient at 0 is equal to 1. I hope that makes sense. So if this exponential function, remember that x being 0, as you know, y exists. So it means that there's a tangent on the y-axis such that the gradient of that tangent is 1. This is what this f prime at 0 means. So, and we find that actually that number is this number e. So that is the number such that the limit of, remember this is f prime, this is the definition of f prime at 0. So that a, if it's e, therefore this f prime at 0, it gives us 1. And this is how we define our number e. So e is that number such that the derivative of that function, exponential function e, meaning e to the power x, meaning the gradient of the tangent of that exponential function add on the y-axis is equal to 1. Let's just, so in a nutshell, we are saying that if we say f of x is e to the power x, so differentiating e to the power x, we still get, remember we said this is equals to 1. We said this is equals to 1. So maybe e to the power x times 1, we get, we said this gives us 1. So basically we are saying that the derivative of e to the power x is equals to e to the power x. So that kind of exponential function is an exponential function e to the power x. So if you look at, remember we said it's a number between 2 and 3. If you look at the exponential function 3 to the power x, and you look at another exponential function 2 to the power x. So there's some function in between, which is e. So e, like I said, is 2.71 something, is an irrational number. So as you can see, this is the number such that the slope, remember when, remember we said we want f prime at 0 to be equal to 1. And we said this means that the gradient when x is 0, meaning on the y-axis, the gradient is 1. So we have this exponential function. So on the y-axis, when x is 0, the gradient, when x is 0, the gradient becomes 1. So meaning the tangent on this exponential function on the y-axis, it gives us 1. So, we get to call this number the natural exponential function. So d dx of e to the power x is e to the power x. I hope that makes sense. So maybe let's take some easy example here. So say you have this function here, y is equals to e to the power x plus 1, and we are asked to find the derivative here. So to find the derivative, remember that e to the power x plus 1, if you get to the same thing as e to the power x times e to the power 1. So e to the power 1 is still e, so basically the same thing as having e times e to the power x plus 1. So from that, and remember I said e is a constant, so it means that this is a function and this is a coefficient, it's just a constant. And remember I said whenever you differentiate a function, you can take out or take out the constant, put it aside and get to differentiate the function. So differentiating e to the power x, we still get e to the power x. So since well, e is an exponent, so it's a constant, so we still have constant times e to the power x, and differentiating 1, we get 0. So this is our derivative. So we can remember e times e to the power x plus 1, then we have 1 plus x or x plus 1. So meaning the derivative just becomes e to the power x plus 1. We have another function here, e to the power x minus x, and we also find the first derivative and the second derivative. So the first derivative, remember that the derivative of the difference of function is the difference of the derivative of those functions. So we can differentiate e to the power x aside. Differentiating e to the power x, we still get e to the power x, and differentiating x, we get 1. So it means that now our derivative just becomes derivative of e to the power x minus x is same, we get e to the power x minus 1. So this is our first derivative. Remember that for us to get the second derivative, it means that we have to differentiate the first derivative again. So differentiating that, differentiate e to the power x, we still get e to the power x. Differentiating 1, we get 0. So e to the power x minus 0 is e to the power x. I hope that makes sense. So now we want to move to more rules of differentiation, or that makes, remember we spoke about the sum rule and the difference rule. So now we get a question, what happens if whenever you have a product of two functions? What happens if, let's say, you want to differentiate x to the power ex plus 1? It's a function, right? Our exponent is just ex plus 1, and you want to differentiate this with, say, x squared. Let's say x squared. Well, one could argue that you can add the exponent to simplify that, but what happens if now we want to differentiate this with 2 to the power x? So let's say you have these 3 functions that you want to multiply. So what happens here? Because now you have a product of functions, how do you differentiate this? Because you can't simplify, say that, same base, because here the base is 2, is not x. So that's why we have this product rule on how to deal with such. So, and please know that depending on what course you're doing or what university you went to, but for most universities, these proofs are examinable. So they get to be asked in your test and in your exam. So please pay attention to this, to what you do. But now to prove it is very easy because we get to use the limit laws. So once you understand limit laws, then it's easy for you to understand these proofs. So let's start with the product rule. So we're saying that suppose you have two functions, f of x and g of x, and these functions individually, they are differentiable. So when you say they are differentiable, it means that there exists f prime. If you were to look at f alone, that function is differentiable, meaning you can be able to find the derivative. Yes, not all functions are differentiable. There are functions that are not differentiable, but otherwise that's a topic for another day. But otherwise, for now, we're going to say that we're going to look at two functions, f of x and g of x, such that these functions are differentiable. So whenever you want to differentiate f times g of x, the rule says keep one function constant, differentiate the other, then plus the one that you already differentiated, keep it constant, then get to differentiate the one that you kept constant. So meaning the derivative of f times g is same thing as f times g prime, or you can think of this as f, or we could say that f times g prime is same thing as f times g prime plus g times f prime. So you keep one constant, differentiate the other, plus the one that you differentiated, you just keep it constant, then get to differentiate the one that you kept constant. And even if maybe we have three functions, f times g times h is the same thing. You mean you keep two functions constant, differentiate the other, then the one that you differentiated, yeah, I hope it makes sense. Let's maybe take for this example. We know that to find ddx, whenever you have y is equals to x cubed, we know that differentiating x cubed, we get x squared. Sorry, yeah, differentiating x cubed, we get x squared. But now, so we get 3x squared. But now suppose this x cubed, you see it as a product of two functions. Because you know that, or you already know that differentiating x cubed, your y prime here, it has to be using the power rule, it has to be 3 times x squared. So you know that this should be our y prime. But now it means that we want to try using the product rule, whereby we have to get this answer. So this x cubed, we get to see it as x times x squared. So, and we say that x becomes our f of x and x squared becomes the g of x. So it means that now we are differentiating a product of two functions. Remember the rule said, keep one function constant, differentiate the other, plus the one that you already differentiated, keep it constant, then differentiate the one that you get kept constant. So if you get to see from what we have here, we keep the x constant, differentiating x squared, we get 2x. So x squared is constant, differentiating x, we get 1. So to simplify here, x times 2x, we get 2x squared. X squared times 1, we get x squared. So 2x squared plus x squared, we get 3x squared, which is the same thing that we got when we differentiated x cubed. So basically, if you just get to show you with an example of what we mean by product rule, that's the application of the product rule. But the part that I want us to get to, I want us to prove the rule. Let's look at the proof. So this is what we claim, that actually whenever you differentiate the product of two functions, f times g of x, you will get f of x times the derivative of g of x plus g of x times derivative of f. So let's start first with the definition of a derivative. Remember that derivative of f of x is the limit of f of x plus h minus f of x over h. But now we have two functions, f of x times g of x. So it means that f of, if you think of this as capital F of x, so it means that this capital F of x plus h, it will be equals to, remember that capital of f of x we said is small f of x times g of x. So it means that this will be, whenever you see f, sorry, whenever you see x, we substitute it with x plus h. So this will be capital F of x plus h, of which that's what we have here. And remember that we said capital F of prime x, it will, by the definition, it will be given by the limit h approaches 0 of capital F of x plus h. This is h, yeah, minus capital F of x, and this is all over h. This is the definition of a derivative. So meaning capital f of x, it will be the same thing as f of x times g of x, of which that's what we have here. So now, please know that there's nothing that we can do here. So what we do, because we want to, remember that this is what we claim. So for us to find the derivative of g of x, it means that we need g of x plus h minus g of x all over h, the limit of that. That is the definition. So we need that aside. So for us to get that, we get to add f of x plus h times g of x plus f of x. So basically these two terms, they cancel each other because as you can see, the other one is negative, the other one is positive. So this is adding and subtracting the same thing. And the reason why we're doing that is because if you look at these two terms, the first two terms, there's f of x plus h, f of x plus h, of which we can factor it out. We'll be left with g of x plus h, then minus g of x. And if we get to look at the last two terms, we have g of x, which is common. So we can factor out g of x and be left with x plus h, f at x plus h minus f of x. Remember, this is all over h. So we can separate this because just to get to write this as two fractions. So we can write this with its own denominator and get to write the other one with their own denominator. So basically this is what we have. So but now the part of g of x plus h minus g of over h, this looks familiar. Remember this, we have limit laws. So using the limit laws, we can distribute the limits. So we can start distribute the limits to the first term and distribute the limit again to the second term. And after doing that, remember that now this limit can also be distributed amongst all these terms. So we can evaluate the limit as h approaches 0 on f of x plus h, and again evaluate the limit to g of x plus h minus g of x all over h. And same thing as for the second term. So you can evaluate the limit of h approaches 0 to g of x times the limit of h approaches 0 to f of x plus h minus f of x all over h. So for that, I believe that this looks familiar. And again, this looks familiar because that's the definition of a derivative. Because here we can evaluate h can approach 0. So h approaching 0 here, we left with just f of x plus 0, which is f of x, of which that's what we have here. So here, this is the definition. This is the definition of g prime at x, g prime of x, which is what we have here. Here, g of x has nothing to do with h. So even if when h approaches 0, g of x is not affected. So that's what we have here. So as you can see from what we have here, this is the definition of f prime of x. So as you can see, then we're done with our proof. And that is the proof. So basically all we are saying that f prime, f times g, the prime of f times g is same thing as f times g prime plus f prime times g. However comfortable that you are, but otherwise it just means keep one function constant, differentiate the other, plus the one that you had kept constant, differentiated, multiply that with the constant, the one that you differentiated is the one that you can now get to keep constant. And that's what you call the product rule. So let's take some examples here. So we have we are asked to find f prime of x whenever f of x is x times e to the power x. So we use the product rule, keep x constant, differentiate e to the power x, plus now keep e to the power x constant, differentiate x. And this is what we get. We can remember that differentiating e to the power x, you still get e to the power x. So hence we have x times e to the power x here. Whenever you differentiate x, you get 1. So we have e to the power x times 1, which is e to the power x. So you can factor out e to the power x, you end up with e to the power x, x plus 1. I hope that makes sense. We have another example here. We have to find f prime at t. If whenever you're looking at the recording of this and it's not live, please try to pause the video and try to do this on your own. So we're given f of t is given by square root t times a plus bt. So remember we said keep one function constant. If you keep square root t constant, differentiating a plus bt, remember this a is a constant, so this becomes 0. Differentiating bt, this becomes b, so hence we have square root of t times b. Now here we can keep a plus bt constant and differentiate square root t. Remember square root t is t to the power half. So differentiating t to the power half, you drop the half, hence we have 1 over 2, then subtract 1. So 1 over 2 minus 1, it gives us minus half, making that to be positive. It becomes 1 over t to the power half, which is 1 over square root t. I believe we've done this example in the previous slide, so I hope this is not a problem. And yeah, that's how we get to use the product rule. We have another example here. We're given that f of x is given by some function g of x times square root x. And we're told that g of 4 is equals to 2. And g prime at 4, we don't know what is this g of x, but we know that g prime at 4 is equals to 3. So now we are asked to find f prime at 4. So first of all, we need to find f prime. So f prime, remember we keep the first function constant or keep one of the function constant. It doesn't matter which one you keep constant first. It doesn't matter. So we kept g of x constant, then differentiating square root x, we get 1 over 2 root x. Now we can keep the square root x constant, differentiating g. We don't know what g is, so we're just going to write it as g prime. So now we can be able to now find our f prime at 4. So our f prime at 4, it means that we have a cx to substitute with 4. So f prime at 4 becomes g of 4, which already been given, that is 2 times. So whenever we see x, we substitute 4, 1. So it becomes 1 over 2 times root 4 plus g prime at 4, of which we've been given that is equals to 3. Then here from our square root x, whenever we see x, substitute 4. So yeah, simplifying, that's what we get. So this is our f prime at 4. I hope that makes sense. So and another thing, for most universities, calculators are not allowed. So you should be able to add 1 over 6 plus, so 1 over 2 plus 6. So for most universities, depending on what course you're doing, but otherwise, whenever you get to do courses like your engineering, or when you get to do maths major, either you're doing some BSc, whereby maths is your major, a calculator is not allowed. I hope this makes sense. Yeah, we have another example here, f of z, and you're asked to find f prime at z. So z is just some variable, there's nothing special to it. So I'm going to skip this example because I can see that we left with 13 minutes and there's still some stuff that I need to go through. So I'm just going to go through this. I'm going to skip this because I believe that you can do this on your own. So please try to work on this problem on your own. We'll get to simplify it later. We have another example here, f of x, which is the product of two functions, x cubed plus 1, and another function is e to the power x, and you have to find f prime and f double prime. So I know that you know how to differentiate polynomial or x cubed plus 1, and again, you know how to differentiate e to the power x. So I'm going to leave this as an exercise for you to try to find f prime and find f double prime. So I'm just going to skip this slide. So like I said, if you listen to the recording, just pause and try to do the question on your own and see if you get the same answer. So there's another question here. What happens if you have 3 factors? So we have 3 functions here. We have 2x squared, we have 3 times x to the power 4, we have square root x. I know that yes, you can write them into the same base, simplify, have one term, and use the power rule to differentiate. But otherwise, the emphasis is to use the power rule. So to use the product rule. So meaning we have to, so whenever you have this, so remember that we can say that this h of x, so we can take 2 functions, combine them to make one function. So it means that now you have 2 functions. Keep one function constant, differentiate the other. So differentiating 2x squared, we get 4x. Remember, you drop the 2, so 2 times 2 gives us 4. 2 minus 1 is 1, so you end up with 4x, keeping that constant. Now you can keep the 2x constant. You have 2x constant, then you get to differentiate those 2 functions that you combined. And remember now we get to use the product rule again here, because now you can open maybe just the big bracket and get to use the product rule to differentiate, keep the first function constant, differentiate the other, just like that. So I hope what I'm saying makes sense. So I'm going to skip over this example because from there it's just a matter of simplifying. As you can see from here, we differentiated 3x to the power 4. Differentiating 3x to the power 4, you drop the 4. So 3 times 4 is 12, subtract 1. We have x cubed. We still kept square root x constant. So now we can now keep the 3 x to the power 4 constant, there it is. So differentiating square root x, we get 1 over 2 square root x. So from there is now just a matter of simplifying. So that's how you get to deal with whenever you have more than 3 factors, whenever you want to use the product rule. I hope what I just said makes sense. So yeah. So as you can see, even if you get to combine this, you want to use the power rule, you still get the very same answer that we got here. Yeah, so now with the remaining 10 minutes, I'm going to try to explain what you have the quotient rule. I doubt we'll be able to go through all the slides, but yeah, wherever we end. So we are saying that whenever you have two functions, one numerator, one in the denominator. So for you to differentiate the quotient, remember that we said whenever from your question paper, whenever you had a quotient, you had to factorize, get to cancel, so that you can simplify the quotient. But now remember that you cannot, not all functions are factorizable. So meaning this approach might not always work. So basically we want to look what happens when the simpler way doesn't work. So we are saying that for you to differentiate f of x over g of x, keep g of x constant, the denominator constant, differentiate the numerator, minus keep the numerator constant, differentiate the denominator all over the denominator squared. Denominator constant, differentiate the numerator, minus, so here the order is important. Remember that from the product rule we said it doesn't matter which one you keep constant, you differentiate, it doesn't matter. In this case, it matters because we have a numerator and specifically we have a denominator. So the rule says keep the denominator constant, so meaning it has to be the denominator. If ever you keep the numerator constant, it's a different thing. It's wrong to do that. So you keep the denominator constant, differentiate the numerator, minus numerator constant, differentiate the denominator all over the denominator squared. So if maybe we just get to use a different notation, this is what we say. F over g prime is something as numerator prime times denominator minus denominator prime times numerator all over denominator squared. So we're going to try to prove this rule and show that it's indeed true. I hope that we'll be left with at least to do one example, but let's try to remember. Let's start first with the definition of a derivative. Remember the definition of a derivative: limit approaches 0, f of g x plus h minus f of g at x all over h. So this is the definition of a derivative. So basically, f over g at x plus h is f of x plus h all over g of x plus h. And f over g of x is something as f of x over g of x. This is the definition. So we want to simplify that. So what we trying to do here, we try to combine, because basically we have two fractions here. So we want to combine these fractions so that we can have only one fraction. So basically, combining the fractions, this is what we have. I hope this makes sense. I hope this makes sense. I hope this makes sense. Yeah. I hope that you guys don't have a problem with denominators, but otherwise what happened here, we just try to do this to write it as one fraction. If in case you're struggling with this, so basically just multiply by, because here in the denominator of the numerator we have g of x plus h, and here we have g of x. So basically you can multiply both the numerator and denominator by g of x plus h times g of x. So if you take this term, multiplying this first term here, the g of x plus h will cancel. So basically it means that we will be left with f of x plus h times g of x. And looking at the second term, the g of x will cancel. We left with f of x times g of x plus h. Then this g of x plus h in the denominator, multiplying it with this h, it will just be h times g of x times g of h plus x. So from what we have here, we add and subtract f of x times g of x, because we want to do the same thing that we did with the product rule. After adding and subtracting, please know that this is the same thing. So these two, they cancel and they gives 0, so we didn't change anything. So looking at the first two terms, as you can see, we have g of x constant, sorry, g of x common, and looking at the second two, the last two terms, we have f of x constant, sorry, f of x common, so we can factor those out. And now, and again, we try now to separate them so that we can have to take h, because as you can see, we have f of x plus h minus f of x, so that should give you an idea. So we can take this h to your numerator so that we have f of x plus h minus f of x all over h. And here, again, remember that we have two fractions here. So we take h to the other fraction here. So we end up with g of x minus g of x plus h over h. But please note that here, there's something wrong, because you're normally supposed to be g of x plus h minus g of x. But here is the other way around. So we can factor out this negative. Because remember that the limit, we can be able to distribute the limit. So doing that, we can distribute the limits. So as you can see, we took the limits to the numerator and denominator. So we looked at the first part of the numerator, and the second part, we distributed the limit, and even the denominator here, we distributed the limits again from the first part and the second part. So upon doing that, remember that if we start looking at this, the limit of h approaches 0 of g of x will still be g of x, because h does not affect, g of x does not depend on h. And here, h approaches 0, we can make h to be 0, we left with g of x. And from what we have here, this g of x is not affected, so we can factor it out. So we can have the limit of h approaches 0 of that. And same thing here, we can take this minus, factor it out so that it can come here, so that we can have g of x plus h minus g of x. So that's that you can see we took out the negative, because that's how we get our g prime. So this f of x is not dependent on the limit, so we can take it out as well. And here we end up with, like I said, g of x remains g of x. Here, g of x plus 0, which is g of x, we end up with g of x times g of x, which gives us g of x squared. So there's our proof. So there's the proof of the quotient function. I hope what I just explained here makes sense. Let's try to get an example. So we have y is equals to 5x plus 1 all over 3x minus 4. So as you can see, we cannot factorize anything to simplify here. So we have to use the product rule. So we have our f of x, which we have our numerator and we have a denominator. So using the quotient rule, remember we said keep the denominator constant, specifically keep the denominator constant, differentiating numerator, differentiating 5x plus 1, we just left with 5. Then minus, keep the numerator constant, which is 5x plus 1, differentiating the denominator, differentiating 3x minus 4, we get 3. Then all over denominator squared. So basically this is what we have. Then from there is the method of just simplifying. And simplifying this, that's what we get. I hope that makes sense. Let's try another example. We want to use the quotient rule. So from what we have here, we have e to the power x as a numerator and x squared in the denominator. So remember that we said keep denominator constant, differentiate the numerator, minus numerator constant, differentiate denominator, all over denominator squared. So remember that differentiating e to the power x, we left with e to the power x. Differentiating x squared, we get 2x. So yeah, then we just get to simplify and we're done. Hope that makes sense. So from here, we can say that, because remember that we can factor out x here, that we will cancel with this one of the x from the x to the power 4, we left with x cubed. So this is our answer here. Let's try the last example of this example. The numerator, you have x squared plus 1, denominator, you have x cubed. So remember that you can't simplify this. So we have to use the quotient rule. So remember the quotient rule, denominator constant in the numerator, denominator constant, differentiate the numerator, minus numerator constant, differentiate the denominator, all over denominator squared. So meaning differentiating this quotient, keeping the denominator constant, differentiating numerator, differentiating x squared plus 1, we just get 2x. Because remember, differentiating 2x squared, we get 2x. Differentiating 1, we get 0. Now keep numerator constant, which is x squared plus 1. Differentiating x cubed, we get 3x squared. All over denominator squared. So our denominator is x cubed, so it's x cubed squared. From now, then it's just a matter of simplifying. So multiplying 2x times x cubed, we get 2 times x to the power 4. Because remember here the exponent here is 1, so 1 plus 3 gives us 4. So here 3x squared times x squared, we get 3x to the power 4. 3x squared times 1, we get 3x squared. So we can add 2x to the power 4 minus 3x to the power 4, we get minus 6 to the power 4. Because now we have x to the power 6 in the numerator, we can factorize x squared in the numerator. So differentiating x squared, we end up with minus x squared, here minus 3. Yeah, I believe the rest is history. So that's about differentiation in terms of product rule, quotient rule, differentiating polynomials, yeah, and differentiating exponential function. I don't know if ever there's any questions. If ever there are no questions, this is where we stop. Thank you guys for watching the videos. I hope they've helped you for you to be able to cope with your first year maths. So basically, obviously, this is not the entire course, but otherwise, we're just trying to give you a glimpse there and there on what to expect. Obviously, there's going to be more exercises, but otherwise, I hope this workshop gave you an idea on what to expect or what is happening from what you took from your high school maths, and to try to show you, including from what we did here with the limits and differentiation, to try to show you on how to go from differentiation of high school to the differentiation of university. Otherwise, this is where I stop. Remember, my name is Dr. K, or you can just say that Dr. Beautiful. Yeah, that's me. Otherwise, ladies and gentlemen, thank you, and this is where I stop. Okay, we don't have any questions.